in one, aren't I? I'm not even on there. Just check the AM one. I think I saw my name on the A1 by mistake. Yeah, someone's put me in the wrong place. That's a good start. I'll put this on the floor as well. Yep. Fantastic. Great.
So James Walton from Jerry is going to talk on the numerical investigation into frictional coefficients and performances of microstructure surfaces. Thanks, James.
Thank you. So I've got quite a lot to talk about, so I'm going to try and hurry up quite quickly. But this part of my PhD is to look over, well, the PhD in general is to look at flow over textured surfaces, but this part is to look at mainly laminar flow. So, how are frictional surfaces useful? Well, here's a report for 2014, which actually the data is based in 2012. Worldwide heavy vehicle consumption of fuel, and you can see 34% is actually down to friction. And of that 33%, 8 to 10-11% is down to transmission and engine friction losses. So quite a large amount, which equates to 180,000 millilitres of fuel globally. And it was stated in this report that textured surfaces or functional surfaces could be of use. So what is a functional surface? Well, we usually randomly create surfaces and usually they are a effect of the cause of some machining. But because of recent technological developments in metrology, manufacturing, we're now starting to control the surface rather than just a random surface that's occurred from the manufacturing process. So here's what I'm going to talk about quickly. So we're going to concentrate really on applying these textured surfaces in a bearing, hydrodynamic bearing application, and we're going to basically predict what kinds of textures we would need to have of any benefit whatsoever. So that's basically what I just said. So previous to this investigation, we did some preliminary work on using the grinding manufacturing method to produce these textures, as you can see here. And you get these very thin scratch marks, and we put these under a white light interferometer, and we noticed that they could be assumed to have an ellipsoidal shape. So we model these as ellipsoidal shapes. So how are we going to model it? Well, instead of modeling the entire bearing, due to the length scales involved in this process, it would be incredibly difficult to do the entire bearing, but actually it's probably not relevant. What we're actually doing is we're just looking at the small interaction here rather than looking at the pressure due to the fact that it's eccentrically loaded. And we call this Couette flow. So Couette flow is basically you've got a stationary wall and a moving wall, and we get this situation here. And if you've got no pressure losses, which is okay for a smooth surface, then you can simplify the highly complicated Navier-Stokes equations to this thing here, which basically says that we have a linear velocity gradient between the surfaces, and then using the velocity gradient times the dynamic viscosity, we then can work out the shear stress. So this is for a non-textured surface. So how do we model? Well, we do everything with open source. Why are we going to use open source? Well, because it costs money, it costs licenses. We just want to make sure that the only cost involved really is the computation, so the hardware. We use something called Salon, which is EDF's CAD tool. And again, this is open source, and inside Salon there's an FE package, there's some CAD package, but we're mainly interested in the CAD package because OpenFOAM doesn't actually have a very sophisticated CAD package. So what we do is we use the CAD package to generate the STL of the surface. we take the STL of the surface and then bring it into our CFD modelling package. The OpenFOAM then takes the surface or the STL geometry file, we create a background mesh, the domain, and then we take away where the geometry is using a snappy hex mesh, which basically what it does is it takes a background mesh, you put your surface in, removes the solid bit which we don't need because we're only interested in modelling the fluid. And then we use simple foam. So simple foam, it's based on the semi-implicit method for pressure-linked equations. It's a very long sentence, but basically what it does, we guess the initial velocity and pressure fields, and using momentum equations, we get a velocity. Then we solve the continuity, get a pressure correction, and the pressure correction then corrects the pressure field, and then we solve again for the velocity field, and we have a velocity correction. So that's what the simple solver does. We solve iteratively until the difference between the previous iteration and the current iteration is 1e minus 8. Then we can say it's satisfied the error that we're looking for. And the corrections are times by an under-relaxation of 0.1 and 0.3. And for those of you who are a CFD knowledge, you'll know that these numbers are pretty low. But what we're trying to do is trying to do a parametric study. What we want to do is leave a package alone and hope there are going to be no crashes. So this basically guarantees that we've got a stable modelling process. By the way, if you want to ask any questions about the CFD solvers, there's lots of different parameters, so ask afterwards and we'll go over if you want. So now we've got Couette flow, and I've described it in the how I've modelled it in the CFD package. We have a no-slip function, which is basically where all the velocities are 0. So this represents the textured surface. And then we have a moving wall, which represents the speed of the bearing. And both the inlet and the outlet of the domain is linked. So it solves and then puts them back over here and keeps doing that, because what we want to try and get is a fully developed flow. And also we do it again in the symmetry, so back and forth as well. So we made a script. So in this script, we submit an array of parametric study. It then works through each line of the array, creates the file structure, runs another Python script, which we'll talk about in a minute, which creates the geometry, sends it to OpenFOAM for meshing, then goes up here, applies the boundary conditions, and then solves it, and then does it again for the next line until it's gone through the array and finishes. And this is the geometry creation script. So this talks to Salom. Using our input parameters, it first creates a film thickness to basically represent the clearance. And then what it does, each line by line in X and Y, it creates a sphere first of 1 or unit. And then you times it by a scale factor which is equal to the length, width and depth of the pocket. And then you fuse that with a box, and eventually you'll end up with a clearance with lots of textures on it. So now we've got a parametric study solver using Python and the other packages we've described. What are we going to put into it? How are we going to optimize these features? Well, we use something called Taguchi, which designs the array. And some of you are asking, what the hell do you use this for? Well, if I was to actually test angle at 2 levels and all the rest of 3 levels, if I were actually to do this study as a full factorial study, it would take about 4,300 trials. Yeah, 4,300 trials takes roughly 2 hours to run the study. That means it would take a whole year to do this study. Yeah, completely out of the question. So what we do is we use Taguchi, which basically creates an array that tests the parameters to the minimum requirements so we can study the effect. So we put that then into using the array that you've just seen, we put that into the software and we get the shear stress results and the lift to drag ratio results. The shear stress results don't give us a full picture because there's form drag and shear stress based in the drag. This, on the other hand, gives us the form drag as well, but also includes the lift, because that's really important because bearings have capacities. So what this shows is it shows the drag and lift, and you can see that for this particular one, the angle which is parallel to the flow is the most suitable and is definitely out of all the others the most dominant. Basically, as you increase the size of the pocket and reduce the pitch, it becomes a more efficient surface. And my pointer stopped working. Then we got all the best and worst combinations of these parameters, and then we ran them again to see what the drag reductions are. If you have the best parameters, then of course we see a reduction in drag. If you have the worst parameters, what actually happens is it increases drag to a normal smooth surface, which concludes with previous research by Said and Sarangi a couple of years ago that conclude if you don't optimize a surface, then don't bother texturing it at all, because it'll increase the drag. So we've got an optimized texture produced 23.3% drag. We've created a script that models these textures and optimizes them. What we've also done by mistake is create a script that actually models any flow over a textured surface. All you have to do is replace the boundary conditions, and you've got an external flow. So actually using this script, you can model any type of flow you wanted. So further work, I've not talked a lot today about the fluids and and the resulting flow fields, but that is some further work, and we're also going to further validate the work we've done with some manufactured samples. Okay? Any questions?
Couple of quick questions for you, John.
You've seen one presentation reducing flow across the surface, and your optimization of the surface is to reduce losses in a circulating system. Now, is the purpose of the textured surface simply to trap some of the lubricant on the surface so that the lubricant
Yes.
slides over?
From a wear point of view, it is, yeah. From a wear point of view, the pockets are also there for other reasons, but from a purely fluid point of view, we're just looking at the oil shearing effect. But of course, from a wear point of view, these pockets trap debris caused in the wearing process. When the bearing becomes starved, when the clearance gets smaller and smaller, there is always oil present there as well, as quite rightly said, yeah. But from a fluid mechanics point of view, what we're investigating here is basically the texture-induced lift from the oil and the oil that's creating the shearing effect. So i.e. it takes less power to drive the bearing itself. Yep.
James, how did you come up with the values for the factors for each of each? And have you noticed any of those factors interact?
Very good question. The parameters that we've got here are actually based on the measured. So we basically ground a surface and we took some measurements of what we could produce in basically by the manufacturing method. And what we've put here is essentially the limits of what we can make. So what we've done is test over a range of parameters that basically say, well, this is the range that we could manufacture. So there's no really much idea behind it. But then obviously when we've optimized it, I mean, what you're seeing here we're not saying it's perfectly optimized, it's maybe just showing the effect, which is probably the better way to say, because I think the only parameter that looked to be optimized in the study was the depth, whereas the rest just showed an effect rather than an actual optimal parameter.
Can we have one very quick question from Abraham?
Yeah, just I wonder, using the Dagushi for optimization.
Yeah.
When on the traction design, experiment Dagushi, is it a odd number or an odd number, such as L8, L16, L64,
Yeah.
etc., or
Yeah.
L9, L27?
Yeah.
What is the idea behind using a zero trial and again L17 as an L16?
Let's have a look.
Yeah,
The zero trial. Oh, it's just the first trial. Is that what you mean?
it's supposed to be one example, then it will be 16 trial.
There are 18 trials there. It just starts from zero. It's because in coding you start from zero. So when you put it into the array, the first row is not 1, it's actually 0. So there is actually 18 trials there. It just starts from 0, that's all.
Okay, thank you very much, James.
All right, thank you.
Our next speaker is Ninjin Trung, and he's talking about trust-based data sharing usage control in smart city.
Sorry. It's open. Yeah, this one. Yeah, thank you. So good afternoon, everybody. So I'm glad to be here to present our research topic on the trust-based usage control for data sharing in smart city. And here's our slide of our presentation. Due to the shortage of time, I just give the overview of our work, firstly with the background on the data sharing in the Internet of Things. And the next one is trust-based usage control mechanisms in smart city, including the trust platform and the usage control using the trust platform. And the last one is implementation prototype. So I will go for background on the data sharing in the Internet of Things. So everybody knows that Internet of Things creates a connected environment among billions of sensor devices or smart devices. Like it is estimated that by 2020, more than 50 billion connected devices are connected to the internet, and that will produce a huge amount of data that we call the big data in terms of 4 V's called volume, variety, velocity, and veracity. And because of the big data, the data can be analyzed from different devices and from many aspects of our lives. So people share data and they cannot understand how that data is collected, aggregated, mined, or processed in order to extract some sensitive information or personal information. So this will impose the data privacy and security in the Internet of Things. And there are some diagrams illustrates some perspective of the data privacy in the Internet of Things. And you can see here a survey from Trustee, and they show the concerns of data owner about their data to be shared, about when, where, and how, with whom the company use the data consumer. There's some detail of the surveys here. And there's, in the left-hand side, the diagram shows that in exchange for data sharing, the data owner will want to get money or time or energy in exchange of the data. And in the right-hand side, this figure shows that who we are willing to share our data to. For example, more than 60% people are willing to share their data to spouse, or more than 40% people want to share the data with close friends, but just 14% for the governments or 14% for the ad companies. Okay, so we will take all of these features into our trust platform in order to calculate the trust in the data sharing. And the question here is how we can enhance the data privacy in the Internet of Things. And the data privacy can be improved by all of the factors, like the consumers, industrial companies, and ours as engineers. So our goal is to create mechanisms to have both consumers to control their data and the companies to express their ability to protect the consumer data. So that is our goal here. So I'm going through to present our solution for the data privacy in the smart cities. And our motivation here is we just share the data with trustful services. So there are 2 questions here. What is a trustful services? And if we have mechanisms to validate that a service is trustful or not, and how can we make an access control mechanism to do that? And for the first question, we will use the trust platform. This platform will calculate the trust value between 2 entities in the smart cities. And for the later questions, we use a new models of the access control we call the usage control that we use with our trust platforms. So firstly, I will present our trust platform. So the trust platform here is, again, to calculate the trust value between two any entities in the smart cities. And in this scenario, we call that the trustee is a service, wants to collect and use the data. A truster is a data owner, that they own the data. And the context here is data sharing, and the environment is smart cities. Okay, so to calculate the trust, basically we collect a lot of information that related to the trust. And from that information, we transform it into the semantic information here. And once we get the semantic information, we will combine with some other knowledge. For example, the knowledge from the surveys that I mentioned before here, and to create what we call the trust knowledge base. So after getting the trust knowledge base, we will use reasoning mechanisms to get the trust value. And once we get the trust value, some decision making could be made accordingly. So to conduct this conceptual procedure, we have to create the trust platform architecture. And this architecture contains of several new components that we will incorporate into the smart city platform. It's called the reputation system, trust broker, trust agents, and trust engine. Okay. And we use some, how can I say, to calculate the trust, firstly we need the trust model. And we follow the trust model, we propose a trust model with 3 trust metrics called recommendation, reputation, and knowledge. And by combining 3 trust metrics, we will get the trust value. So that's approaches we get from our idea. For example, if we, in the human idea, for example, if we about to buy a car, and you are look for many cars, many models and brands, and you will choose what is the best cars for you. And basically, you will find some information, for example, in the internet, in the advertisements, and that's we call the reputation. You also ask some opinions from your friends for colloquies and about the car that you want to buy. We call it the recommendation. And you also, based on your knowledge about the car, for example, some factors like energy consumption, something like that, we call it knowledge. And by combining 3 kinds of factors, we will calculate the trust value. And in the networking environment, this can be done by using some semantic web technologies that we use here. For example, this is ontologies for representing the trust models in a machinable, readable way. Some technologies for representing and publishing data, and reasoning mechanisms for getting the trust value. And once we get the trust value, we will use it for the usage control conceptual model here. So the trust value will be here as a condition for the authorization here. And combining with the data consumer attributes and data owner or stakeholder attributes, we will get the authorization here. So the conceptual models we propose basically in this kind of diagram. And to implement these models, we create the architectures incorporated with the IoT shared platform in the smart city here. You can see this uses control mechanisms here, our trust platform here, and there's some kind of mutual components here. And for the implementation, we are going to implement it is ongoing work, and our implementation architectures here is some sensor for getting data. Here we use some simulator like CoApps or DPWS. And the gateway is at the Tomcat server and our chef platform here. We also need to put this thing in the cloud by using the OpenShift platform. And that is the end of my presentation. Yep.
Any question? No? Right. Well, I've got a question for you.
Yeah.
When you actually develop your system and you have those 3 parameters, now, most of the actually trust when it comes is that people actually hackers or anything like that. What happens is that it takes time and sleeping time before they try to attack. And therefore, do you think your model could actually have an effect in this case when there are actually sleeping, actually what we call them usually the sleeping attackers?
Actually, I don't get the question here.
What happens is that when you're looking at your model, and we have actually the trust model, yeah?
Yeah,
the
here.
other one, yeah, this one. So you have 3 parameters, yeah?
Yeah.
And 3 implementation, one of them is the trust, and you said that how actually people how it actually is going to be used for a period of time, then this will actually build a trust, yeah?
Yeah, right.
Now, if you're talking about what we call it is sleeping attackers, then they do nothing, and you can feel that they are actually trusted, yeah? And then there would be an attack. Is that going to be affecting your model, or this is not actually related to what you're doing here?
No, it's not.
Right.
Yeah, fake. This here is actually we don't. How can I say? This is not the parameter, but this is some kind of things that we need to calculate. And we base on many kinds of characteristics from the network environment to calculate this one. Yeah.
Okay. Thank you. Thanks. Thank you. Our next speaker is Neil Nethergaard, and is actually going to give us a talk about a new approach to quantify whole body mechanical load from trunk accelerometer.
Just give me a second. Delete button. There we go. All right, you can do your magic. All right. Thank you. I guess this is my slides already. Oh, sorry. Yeah, the clicker. Yeah, fine. All right. Now you can just have more time to look at my slide, and as some of you may have discovered already, it says the RISES, so the Research Institute of Sports and Exercise is where I'm actually based and where I'm doing my PhD. But it's in collaboration with the Applied Mathematics department, where we have Paul Lisbour and Board on my supervising team. So we thought this would be a good opportunity to actually show some of the cross-discipline work that we're doing here at LTMU. So from a sports scientific point of view, if you look at a coach on a daily basis in training, what he'd do is he'll go out there on the pitch, he'll watch whatever the players are doing. He'll then do some kind of analysis of that based on what he sees, make a new plan of what's going to happen in the following training, whether they need to train harder, whether they need to give them a rest because they're fatigued, and then implement that new plan. And then circular goes on doing every training, doing every day when professional athletes train. But this analysis is based on subjective measurements, and that's where sports scientists as myself come in, try to provide objective measurements that can help the coach in his decision making, basically. So what type of objective measurements are we doing? Well, like the rest of the world at the moment, wearable sensors seems to be the newest thing. We've moved on from just monitoring heart rate and now using these GPS sensors, which players wear in this vest during every training on the back of their trunk. And then we basically monitor everything they're doing. We're the big brothers in sports science and collecting a lot of data there. A newer thing that we begin to look into is the inertial sensors and the data we get from that. So basically, we get a lot of data that we as sports scientists not necessarily are that good at understanding, and we are not used to working with that amount of data. But generally, why do we do all of this data monitoring in the sports world? Well, we want to make sure that we adjust our training, so we adjust the intensity of our training, the volume of our training, and how often we train, that we reach those physiological adaptations that we're after that will improve our performance. So we want to make sure that that training load we expose the players to will improve their performance. On the other hand, we don't want to go into a zone where we get the players at risk of an injury by either increasing the intensity over time or training too long, because then we'll have that injury. But as you can see, it's a really narrow edge there between getting performance enhancements but also reducing risk or having a potential risk. And the way we do in sports science, and what most sports scientists understand, is what we call metabolic load. And it's something that's been explored for many years and we're really good at. The easiest way to explain for you guys, I guess, what I mean by metabolic load is if you think of a player as a car will travel from one point to an end point. And what we do with our GPS measurements then is we measure the distance they cover, the velocities they run at, how much high intensity have they been doing during a training session, because high intensity running is related to performance. So you can see in some way, what we measure with that is basically what the engine is doing. So is our engine prepared to cover that distance we want it to cover? Can it run at that velocity we want it to run at in the game? And then at the same time, how is that related to the fuel consumption of our engine? Are they getting tired? Are they having enough rest that we can refuel the engine and they can do what we want? And that is what I would say 99% of the data that we collect in professional team sports nowadays, that's used for as a metabolic load. The other thing you could look at is actually the mechanical load. So if you think of the mechanical load of a player, again, you relate it to a car, you have your car riding from one point to an end point. Within there, there's some speed bumps. Those speed bumps are absorbed of something. If you think of a car, then it's your shock absorbers that absorb those forces that it's exposed to when it runs over the shock absorbers. When I move around, when you run around, you generate forces to run around, but you also absorb forces from the ground. And it is our muscle, ligaments, bone that absorb all these forces we're exposed to. But if that stress gets too high, just like it would get on a spring over time, that spring would damage. It means we have to put our player back into the garage, we'll repair it, and then we'll be ready to go out on the pitch again. But we don't really understand much about this because we can't monitor it in the field at the moment. The only way we really can monitor those forces, so the ground reaction forces acting on the body, is in the lab where we have a force platform. Typically we just have a series of one force platform and then we can measure one strike and then we'll have to repeat it. So it's really different from actually what happens out in the real world. As I mentioned, these sensors now have inertial sensor, or the GPS sensors also have an inertial sensor in it, including an accelerometer. So what the companies have come up with now is that you can actually estimate the forces, or they assume that you can estimate the forces based on Newton's simple linear relationship, Newton's second law of motion, with the linear relationship between mass times acceleration is equal to forces acting on the body. But for that to happen in a real scenario, the case would be that the trunk accelerometer that we mount on our players should actually represent the center of mass, because the only thing that can tell us what forces are acting on the whole system would be the acceleration of the center of mass. So it's important that those trunk accelerometers measure the center of mass acceleration of our player. Unfortunately, we just recently published this paper showing that this isn't the case. So you have the black line here would be the center of mass acceleration, then you have different colors depending on where you put that accelerometer, because there is a general assumption that you can change the location of your accelerometer to get so close to what we think is the center of mass. But unfortunately, regardless of position, it doesn't happen. Our body is a multi-linked system, so if I move something, my center of mass will move. We can't just attach an accelerometer to a center of mass. So basically, the approach we're using nowadays isn't enough to monitor that mechanical load that is related to the stresses on our soft tissues. So we had to go back and think a little. And if you think of running in general, it's a bouncy movement. It's like Tigger on a poker stick, bouncing up and down when you run. And the simplest way, basically, to model that as a linked model system would be a double spring mass damper model system. And it has been used in the past to determine ground reaction forces, so the forces acting on the body. And what you basically need to know is you need to know some 8 model parameters to tell you something about the behavior of that model. And then when you go from if you know the acceleration of the 2 masses, then you can get the ground reaction force. So if you solve that double differential equation and having those parameters available, then you can actually get a reliable ground reaction force. And ground reaction force is similar to the ground reaction forces we measure in our lab. But the typical approach with these type of models is that you actually go into the lab, you measure a contact on the force platform, and then from that contact, you get the 8 parameters, and then you might estimate it over a number of steps. So that still doesn't solve our problem of coming out in the real world and collecting some data. But I started talking about the accelerometer that can measure something about the trunk. So what we actually come up with, instead of using measured ground reaction forces to estimate the ground reaction forces, we're actually using the trunk acceleration that we measure out there in the field. So in this case here, it's just 1 foot contact, where you have the gray line here is the measured trunk acceleration. The black line is the measured ground reaction force from the lab situation, same step. And then we use the acceleration we know to drive the spring mass model. And we do that by a gradient descent optimization, where we optimize the blue dotted line here, the acceleration of the upper mass, to the measured acceleration out in the field. And then from that optimization, we then get our 8 parameters that we need, and then we can calculate our ground reaction force, or at least get closer to it. So that's where this approach here has moved a little bit forward, because we've advanced the whole thing about spring mass models in sports science, and not just using ground reaction forces or kinematics, but we're actually using something now to run these models from data that we get on a daily basis in every training. So my take-home message from this will basically be accelerometer on its own isn't enough to measure mechanical load in the field or the whole body. Again, an accelerometer will just measure the acceleration of whatever second we attach it to in the field, and that isn't enough for us. We need more advanced techniques, and that's where guys like you can basically help us to understand better how we can model our systems and better model those mechanical load in the field. And why is it so important then to get that ground reaction force? Well, that ground reaction force and that mechanical load could give us valuable information that we don't have available at the moment about the risk of those injuries. Finally, I just want to thank you, acknowledge my supervising team, as well as my funding here at LGMU, the Football Exchange, as well as a UEFA grant that we were given back in 2014. Thank you for your attention, and I'll be happy to answer any questions you might have.
Do we have any question? Yeah? Yeah.
It's a very interesting area of research, because given the complexity is relatively common. I'm interested in how do you validate these models?
Yeah.
Yeah,
I was running a bit quick. So basically what we did in this approach here was that we had our players coming into the lab. They were wearing a trunk accelerometer, but there was also a force plate available. So we basically measured that force plate, the black line here. So that black line there is the force plate data. And then we could the blue line here is then the estimated ground reaction force we get from our model when we're using the trunk acceleration as the input. So that was basically our validation. So we had something we knew, or we knew the actual ground reaction forces for this type of data.
Do you have any one quick question? No? All right, thank you very much.
BJ,
I think we can, quite pleased, we can start the closing of the one-week research conference. It has been a very successful and constructive conference over the week. Over this research conference, we have had 6 keynote addresses, more than 90 oral and 40 poster presentations, and 1 elevator pitch session. By any standard, it has been a very successful event. This year, we have used YouTube to televise every session. Wherever you were, you could see every presentation. Indeed, even you missed any chance to listen to any presentation, you can still visit YouTube to look at every presentation here, right? So that can keep you busy in this weekend. Now, if you look at engineering and technology research, really, it is a very important subject. It has penetrated in all the areas of everyday life. Of course, you know, if you look at this particular conference, we have covered a wide scope of engineering and technology subject areas. As a faculty, we take all the researchers as very important assets. We do all our best to support every researcher in order for them to realize the potential and also achieve the research development. To benefit any engineering and technology applications, it's really important for the researchers to share the research findings and experience. So we have had this research conference. This is our 2nd time to organize this faculty-wise conference. Compared to the last years, I think this year we have organized this conference in a much better way. We support PhD students using whatever we have. If you look at these faculty's PhD members, we have well over 200, accounting for more than 1/3 of the university's PhD members. If you look at this month, the faculty has allocated 15 PhD studentships, 12 for home students, 3 for international students. The university has allocated another 7 to support our PhD research. As time goes, of course, you know, there will be more funding allocated to support the PhD studies. I think we are moving to the closing of the conference. I don't want to talk too much. But today, we have a kind of award-giving ceremony. In total, there are 5 categories for awards. That's best paper, best presentation, best poster, best elevator pitch, and best potential impact. And today, we have our Vice Chancellor for Scholarship, Research, and Knowledge Transfer to present all the awards to the winners, Professor Robin Leatherbury.
Thank you very much. It's a great pleasure to have the opportunity to come and see some of the people that are actually participating in research. If you think of the different categories, I think we all appreciate that high quality publications are something that the external world uses to judge us, and how you present yourself in papers, in posters, is obviously extremely important in developing you as future research leaders. I'm very struck with the emphasis on something which is increasingly important in the funding context, which is impact. Back in the day when I was doing a PhD, you turned up, you went into your lab, you never talked to anybody, you came out at the end. Nowadays, it's very important to be aware that you have to communicate your research. You have to transfer your knowledge to the outside world, and it is in terms of the impact that frequently we are now judged. So I think the impact as a category is very important. An elevator pitch. I suppose that what we are doing, if we were in competition, I'm sure we would not have come out well in the elevator pitch, because it's again an extremely important skill. And if you're involved in enterprise, you may have to sell your work, your concept, your idea to someone that would be a funder, or for that matter, if you're at a party and you have a couple of minutes and somebody says, "What do you do?" Well, you've got to be able to summarize that. And it's a skill which is not perhaps traditionally brought out in a research lab, and you have to make sure that you acquire these skills as part of your research training. Research, enterprise, knowledge transfer, these are viewed as extremely important within the university. And we are taking forward the supporting of further PhD students, of encouraging staff to get involved in research. And so being in this room, packed, we even have people standing at the back, it's a great pleasure to see the enthusiasm for research, which is quite obvious. Now I suppose everybody that participates in research gains a prize and recognition from that participation. But in life, of course, there are prizes, there are winners in each of these categories, and I'm not sure whether we have some anticipation in the audience, whether you have perhaps prepared your Oscar speech for your acceptance. Don't think we've got time for you to do that, but we do want to recognise excellence where excellence is due, and we have the categories that were mentioned before, and we have 3 prize winners in each category. Of course, everyone is a winner, but some are better winners than others. And everyone receives rewards, but perhaps those rewards are less tangible and less financially benefiting the recipient than the rewards which I believe are tucked away in white envelopes that will be distributed. So, I will let Jin read out the categories in turn, and then we will go in reverse order, in true Oscar style, from third through to the winners. Jim.
Thank you, Robin. The first category, that's Best Elevator Pitch Award. In this case, we have 2 joint third awards. The first third award goes to Mr. Sam Walton from Astrophysics Research Institute.
Congratulations. There we go. You can now go and spend it.
Right, the second third award in Best Elevator Pitch goes to Mr. Vajikumar Kulumudzi, Department of the Skill Development. Now it goes to the second award. Second award goes to Miss Jessica Liu, Department of Computer Science.
Congratulations, Jessica.
Thank you very much.
Here we go.
Very picture.
Now the big prize, the first prize winner, the first prize goes to Miss Lucy Horner. Now we move to the second category, that's Best Poster Presentation Award. Again, we have joint third awards. The first third award goes to Mr. Simon Prentice, Astrophysics. The second third prize goes to Mr. Enmar. The second prize goes to Mr. Ross Kelly, Applied Math. The winner, the gold medal, goes to Mr. Reggie Hardy, Computer Science. Now we move to the third category, that's Best Paper Award. We only have a single third prize winner this time. The winner goes to Mr. Mohammed Usman. I think Mohammed is not around today, but he's designated somebody, Dr. Cheyenne Kawakaw, to pick up the award. Please. Prize goes to crystalline vacuum built environment. Now, the biggest winner in the Best Paper Award goes to Mr. Niles Nethergard, Sports and Math. We move to the fourth category, that's Best Potential Impact Awards. Firstly, again, we have a single third award this time. The third prize goes to Mr. Mورس from Maritime Engineering. I think Mورس is not around. He has designated Cheyenne Kawakaw to pick it up. The second award for Best Potential Impact goes to Ms. Enmar, Civil Engineering. The winner goes to Mr. Khalid Hashim, Built Environment. Now, the last category, that's Best Oral Presentation Awards. The third prize goes to Niles Nethergard again. Now we move to the second prize winners. This time we have joined second prize winners to make a difference. The first, second prize goes to Adini Olumide from Ghana. The second prize winner goes to Mr. Hussein Jaffer from Civil Engineering. Now, the last winner. The winner for best oral presentation goes to Tabia Mohammed Curry. We have a special prize to be given. We know that this conference has been organized in such an exciting way. The organizing members have put so much effort in organizing such an exciting event. So a special prize will be given to the organizing team.
I think it's great to see all these prize winners. I fully anticipated, or perhaps I didn't anticipate, that in a faculty which is going to be more numerate than the rest of the faculties, where mathematics plays a very important part, somehow you didn't feel constrained to have integer numbers of first, second, and third prizes. That we had a first third, and a second third, and a first second, and a second second, possibly in keeping with the traditions of an academic background where we award first class and then first second class and second class and third class degrees. It's highly appropriate that we should therefore have varying categories of first, second and third prize. However, I really do think that the winners from this are not just the people that walk off with the most prizes. We have a couple of people that have got more than one prize. It's great. Try and get us even more next time. It's okay. We'll have another one next year. But the winners are people that are participating in the research. And I think it was really nice. I didn't know we were going to acknowledge the team that put this together. But it is a big job to try and get this sort of event organized. So I think it's great that effort is recognised appropriately. Thank you very much for letting me give out your prizes. I'll pass you back to Jim, who will wrap up the event.
Right, I don't want to spend any more time in closing the conference. I just take this opportunity to thank all the participants for making such an event so successful. In particular, I want to thank the organizing team who has put so much effort and time in organizing this successful event. And also my thanks are given to those from outside the country, Ukraine, Malaysia. They present in the keynote addresses, they share their experience and findings with us. So thank you for everything that has been done. In the end, I just close the conference. We still have 1 hour social session, so if you want to continue to network with each other, please do so. Thank you very much.